Doctor.
Okay, so we were saying that we can conclude this by seeing the difference of order of magnitude. So the difference of order of magnitude between 1 and 100 is the order of magnitude difference is 2 power 3. Okay, so if I can add to 1 here minimum 2 minus 4, then I can add to 1000 2 minus 1. هلا pay attention. هلا هون اوقات ما بتكون على القد، يعني مثلا اذا بقول لكم what is the minimum number to add for 1001 حتضلها 2 minus 1. اوكي، يعني انا بشوف ال difference of order، مش ضروري تكون على القد انه 1 times 2 power 3، لانه اذا برجع بعملها لل 100 لل 1001 بالباينري. Okay, if I do the analysis, I put 0.10010 times 2 to the power 4. Okay, it will be also the minimum number that could be added to it حيكون 0.00001 times 2 to the power 4 يلي هو 2 minus 1. Okay, يعني هيدا المينيمم نمبر مش بس is the minimum number to add to 1000 كمان to 1001. Okay, أو maybe to other numbers depending on the case. Okay, so هي فكرة إنه the difference of order بتكون of the order of 2 power 3. Okay, يعني مثلا كمان إذا بحط نمبر ثاني، إذا بحط لكم 1101 كمان the minimum number to add to it هو 2 minus 1. كمان إذا بعطيكم 111 1111 كمان، يعني ال difference of order لأنه هون عندي 1 digit، هون عندي 4، يعني ال difference ك order of magnitude هو ال difference 2 power 3، بس هي منا exactly 1 times 2 power 3، بس بمجرد ما هون عندي 4 digits هون 1 digit، يعني ال order of magnitude is different to the order of 2 power 3. Okay. Any question, any additional question on this?
دكتور يعني أنا ما بيهمني إذا 0 ولا 1، أنا بيهمني عدد الديجيتس هو my focus. ولا
Yes، يعني أنا قصدي إنه ال minimum number that you can add مش بس هيدا ال 0.0001 مش بس هو ال minimum number to add to 1000، كمان هو ال minimum number to add to 1001 to 111 etc. يعني to يعني هيدا النمبر مش بس هو ال minimum to add بس to 1000، كل حيلا نمبر نفس الاوردر of 1000 the minimum number to add to it حيكون هيدا. اوكي، يعني اذا بتاخدي هيدا النمبر او بتاخدي 1 نفس الشيء، شو هو المينيمم نمبر you can add to it اذا الكمبيوتر can just store this number of digits حيكون 0.00001. اوكي، لانه هيدا already number عنده 4 digits، يعني انا وقتها بدي زد له حيلا شيء ومينيمم زد له، اجباري يكون هالنمبر هون، يعني يوقف هون، لانه اذا النمبر عنده ديجيتس لبعدين هوليك ما حيقدر يقريهم الكمبيوتر، لانه ديجا هو حجز 4 ديجيتس هيدا النمبر 1 2 3 4، يعني the minimum number that I can add to it بده يكون 0.1. اوكي. Yes, I will repeat the minimum number to add. Okay, look, هي الidea is شو يعني it is the minimum number to add؟ يعني if I add any other number that is smaller, the computer cannot read it. It cannot read it. Okay? يعني أنا عندي 5 digits. في عندي several methods to know what is the minimum number. إذا أنا بقول لكم عم بعطيكم example مثلا what is the minimum number to 1100 والكمبيوتر عنده 5 digits. Okay? already النمبر اللي أنا أعطيتكم إياه already في 4 digits 1 2 3 4، يعني أنا already مجبور، أنا حاجز 4 digits، يعني إذا if I want to add something that is very small ما حيكون يقدر يكون أصغر، يعني ما حيكون في أصغر من 0.1، لأنه إذا بصغره أكثر يعني اعتبروا أنتوا عم بتزيدوا 0.0 something، whatever is this number after here, it will not read, the computer cannot read it. Why? لأنه إذا بدي أكتب 1100 in standard way هتكون 0.11000 okay times 10 to the power هون 2 to the power 1 2 3 4 okay يعني انتم بمجرد ما اخذتوا هيدا النمبر كله لورا يعني بدها تكون 2 to the power يعني انتم اذا ترجع هيدا الزيرو بدي times 2 to the power 1 times 2 to the power 2 times 2 to the power 3 times 2 to the power 4 صح؟ so already عندي هون times 2 power 4 okay now what I will do sorry 2 to power 5 حتى هون لأنه عندي how many لا سوري مظبوط 2 power 4 لأنه ديجا عندي 4 digits اوكي وبدي رجعهم لورا الزيرو بوينت يعني 2 power 4 what is the minimum number I can add 0.0000 إذا هون بحط 0 يعني I cannot see anything at least it should be 1 okay يعني أنا the minimum number that I can add to this one هو 0.00001 هيدا النمبر اوكي هو 2 to the power minus 5 times 2 to the power 4 هو 2 to the power minus 1 اوكي حتى انا بلاقي هالميثود اهين اول ميثود اهين من تحطوا ستاندرد فورم لان دغري بتقشعوها already هالنمبر reserved 4 digits okay so I cannot add a number smaller than 0.1 لأنه if I add 0.0 something ما حيقشعوا الكمبيوتر لأنه look عندي 1 1 0 0.0 هولي already 5 digits 1 2 3 4 5 إذا بزيد 0 point إذا بزيد 0.0 something okay الكمبيوتر ما حيقرا الباقي هون حيعتبر انه عندي 0 plus 0 0 اوكي وحيرجع يقرا النمبر as it is so it will not be able to add a number if it's smaller than 0.1 بينما اذا بس باخذ 0.1 بيقدر يقرا الاديشن لانه 0 plus 1 is 1 so بيقدر يزيد لي 0.1 to 1100 اوكي if
دكتور مش فينا
yes.
سوري مش فينا نعملها دغري يعني هلا نحن مونتال اذا بتقولي لي 11 11 و it can store 5 digits كم بعد بدي digit
مظبوط اذا 11 فيك تحطيها like this 11.001 لانه already ال 11 حجزوا 2 digits 1 2 يعني قد ايه بقى لي بعد الدوت بقى لي 3 digits يعني the minimum number I can read هو 0.01 yes you can do it like this يعني you can say already هون عندي 2 digits so I can add minimum 0.001 يعني I just have minimum 3 digits after maximum 3 digits نعم
سوري شو الفرق اذا كان ال 11 هو باينري او ديسيمال انه كيف معقول تقولي لنا تنشوف
اذا الكمبيوتر is working in binary system ورجعت قلت لك what is the minimum number that I can add to this number but express it in decimal base يعني بس اخر شيء بتقولي لي انه 0.001 in binary okay is equivalent to 2 minus 3 in decimal اوكي يعني انت عاده معوده تشتغلي بالديسيمال يعني انت ال 11 عندك هو 1 plus 2 هو 3 اذا بسالك السؤال the computer is working in binary system what is the minimum number in decimal that can be added to the decimal number 3 شو بتعملي بتحولي 3 لباينري 3 بالباينري بتكون 11 بتلاقي the minimum number in binary that can be added to 3 وبترجعي بتحوليها لانه طلبت منك الريزلت ان ديسيمال بتحوليها لديسيمال بتطلع 2 minus 3 يعني the minimum number that can be added to 3 هي 2 to the power minus 3 يعني 1 over 8 اوكي any other question on this
yes.
حدا بعد عنده question على البريسيجن او المينيمم number to add Okay. So we are done with the correction of the assignment. So we will start together a new chapter. Okay. So you are responsible for the exam of just chapters, chapter 1, introduction, chapter 4, 5, and 6. I posted an assignment for you to practice on 5 and 6. Okay. But now we should start with a new chapter, which is uh, solving of linear systems. Okay. So this chapter is called Gauss elimination. It's a technique used to solve a system of linear equations. And you will see that it's a very important chapter because we will use it in many other chapters. Okay. And our purpose is to develop techniques to solve for a system of equations, a linear system of equations. So first we will introduce how we can solve a large system of linear equations using a first method, the Cramer's rule, and then we will introduce a second method that is more efficient on يعني وقت أحكي efficiency here I talk about time because I want to reduce the computational time of the method. So this is called the second method we will introduce in this chapter is Gauss elimination. We want to appreciate what is the efficiency of different methods. We will see that Gauss elimination will allow us to solve a lot of computational time compared to Cramer's rule. So Cramer's rule will be only limited to cases where we have a small number of equations, 2, 3, not more. And we will understand the implication of ill-conditioned systems. We will understand what is the meaning of ill-conditioned system and why, in this case, we cannot, if we change a little bit, the result, the solution will change a lot. So we cannot trust a lot the solution. We will see what do we mean by this in some examples. So to start with, before starting with the methods, with the numerical methods to solve a linear system of equations, we will just see several engineering applications that involve a use of solution of a linear equation system. One simple example is the case in mechanics. If you take two masses and you have springs connecting them, and you want to solve for the displacements of your masses, x1 and x2, if knowing the forces applied F1 and F2. If I'm working in equilibrium conditions, so you know from statics that the force developed in a spring is equal to K times delta L. And in case I have equilibrium condition, F1 should be equal to K1 x1, while F2 should be equal to K2 times the displacement of delta L of spring 2. And as you can see here, considering that the springs are originally unstretched, so when M1 and M2 move, the displacement delta L of the spring will be the difference between x2 and x1. So this is a simple example where I have to solve a system of two equations with two unknowns. Here it's a very simple system. I can solve for x1 from equation 2, then replace x1 in equation 1 and solve for it. Okay, but what if I have a high number of masses and a high number of springs? So if I can increase the complexity by adding springs. So here, for example, if I add a spring here, then I will have the equivalent stiffness of my spring here will be K2 plus K3. And if I have a lot of masses and a lot of springs, I can end up with, let's say, a system of 1,000 equation with 1,000 unknowns. So it's not feasible to solve it by hand or to use very long methods. Okay, so then we should go to efficient techniques that can solve such system in a fast way. So in general, we can write such problems in this way. First, we have a matrix representing here, for example, the matrix will be, the first matrix will be the matrix of stiffness of my spring. So it is related to information of my system, okay, of properties of my system, times the vector of unknowns will be the displacement vector in this case, equals to the external forcing that is applied on the system. So here it's the forces applied. Okay, and we will see that in several applications we have the same form. And we have a matrix concerned with information on the system, a matrix of a variable related to the system. Here it was the position, and equal to what we impose on the system. Here it's the forces. If we take another example, another field, okay, let's say you have a space where you have several zones connected to each other, and you want to determine what is the concentration of a certain species uh, inside these zones. Okay, so this is, for example, it can be considered as an indoor air quality application or chemical engineering application. So here the stiffness will be replaced by the exchange between zones. So because it's information about the system. So this is related to the system, the exchange between zones, while the force vector will be replaced by the if you want, the interaction between the outdoor and your system. So here the flow rates going inside and going outside, so which represents the interaction with the external environment will replace F vector, while the position vector will be replaced by the concentration vector. Okay, so this is a second application where we can also have a linear system. In this case, instead of K, we will have K will be replaced by here the effect of flow exchange and mixing between rooms, because this matrix will always be related to information on the system without taking into consideration external effects. Here, the unknowns will be the concentrations in the different zones, and the external effect here will be the flow rate of exchange with the outdoor environment, so inlets and outlet flow rates. Here, a similar example can be given here. You have several tanks that are connected to each other, and you have flows that are coming from outside. So you have inlets and you have outlets. So here it's very similar here to the previous examples. Your first matrix will be the one including the exchange between your tanks. Okay. Your vector of unknowns will be the vector of concentrations equals to the what you have as input and output to your system, which is exchanged with the external environment. So also here, same equation. Okay. Another example is an electrical engineering application. So you have a system of resistances, and you have current that is going through the system, and it can be, that it will be divided. So here you can write a relation between the current passing in each line, function of the resistance, okay, and voltage. So this can be written also in matrix form. And here you have that the effect of resistance and connectivity between nodes, which will be here. There is information about resistances. You have now your unknowns will be the current in different parts, and the external information on from external environment on the system will be the voltage. So all of these applications here all can be written in same form and involves the solution of a linear system of equations. This is why in this chapter we will develop several techniques to solve for a system of linear equations. We will start by the easiest system with two equations with two unknowns. In this case, we have four possibilities. We can have a unique solution, we can have no solution, we can have infinite solution, or we can have a nil condition system. To understand the difference between these four, we will do a certain graphical representation of these two equations to know what are the possibilities of solutions that we might have. The first possibility, which is the most common one, is a unique solution. So you have two lines that will intersect each other. So they can be represented by a system of two equations with two unknowns. Each equation will represent the equation of the line you have here. And you will get then, if you draw it graphically, the two lines will intersect at one point, which will constitute your solution. This is the first possibility. The second possibility is to have parallel lines. So if you draw your this equation and this one, you will have two parallel lines that will never meet. In this case, you can say that you don't have a solution for your problem. And you will see that this is characterized by a determinant equal to 0 of the matrix formed by the coefficient. So here, matrix A So in general, we write the system as A times X equals to B. So if you want to represent the system in matrix form, it will be like this. The result is 110. So this will give you 110 as column of results. You have x1 is multiplied by this column, which represents the coefficient of x1, will be represented here as 3, 3. And here you have the column of x2, minus 1, minus 1. Here, if you do the determinant of this matrix, you will get 0. So when you have a determinant of 0, you can have or no solution or infinite solution. So we will see in next slide the case of infinite solution. So in case you have here, for example, the second equation is a multiple of the first. So if you multiply equation 1 by 10, you will get a different equation, but if on a graph, it will be the same equation because this equation is a multiple of the first. So they constitute in reality one equation. And then if you draw them on a graph of x2 function of x1, you will get the same line. So here you have infinite possible solution. Any point on this line will be a solution for this system. Okay, and again, if you calculate the determinant of this matrix, which is the matrix A will be 330 and minus 1 minus 10, it will be 0. So we will see in general that when the determinant is 0, a numerical solution will induce problems because you will have cases of no solution or infinite solution. Now, the fourth possibility is to have a nil conditioned system. If I have a nil conditioned system, what do we mean by this? This is very close. This system will be very close to infinite solution, but with just a very small difference. And here, if you have infinite solution, the coefficient here should be 10, and the result should be 10. If I just changed by 1%, okay? If I change by 1%, here's the result. So instead of 10, I put 9.9. I will obtain a solution for my system. I will get an intersection point, but as you can see, the two lines are very close to each other. Why we call it ill-conditioned system? Because now, if I put instead of 9.9, 9.8, I will get a very different result from this one. So I cannot trust my result with 1% uncertainty, okay? And this will cause a certain problem for me. Okay, because if I am not just uncertain 1% of the result, my solution will be much more different. Okay, and this is called ill-conditioned system because any small variation in the number here will cause a very high variation in the solution. So I cannot have a small range of uncertainty in this case. Now, let us see what is the technique, the common technique, okay, if we want to solve a system of two equations with two unknowns using Cramer's rule, okay? Cramer said that in case I have a linear system, I can replace it first by a matrix form, which will give me the equivalent system. The method is very simple. I write my system in this way. I write the first equation, the second equation, and I put x1. Yani, I should have always, if I started by x1 in the first relation, I will start by x1 in the second, plus a coefficient times x2 equal to b2. So I write them in the same form, and then I can consider that the coefficients multiplying x1 will constitute the first column of matrix A, and the coefficients multiplying x2 will constitute the second column of matrix A. And then my matrix A will be multiplied by the column of variables x1, x2, which will give me the column of results b1, b2. And you can verify this because when you multiply matrices, what you have is that you do this. You do a 1, 1 times x1, plus A12 times X2 equals to B1. So this will give you equation number 1. And second step, you do A21 times X1 plus A22 times X2 equals to B2. This will give you the second equation. This is why we can say we can replace the system of linear equation by a matrix form. Now, whenever I did this transformation, I can solve my system using Cramer rule. What is Cramer rule? So Cramer said that I can calculate the determinant of this matrix, and the determinant is calculated in this way. So this is the simplest matrix that you can have. To calculate the determinant, you start for the first element by a plus sign, and for the second by minus. Here it will not, in this case, it is very simple. It will be plus A11, A22 minus A12, A21. It's very simple. But if we have more number of elements, the computation of the determinant will become much and more complex. Okay? So now Cramer stated that if I want to solve for this system of two equations, two unknowns, I can come up with a very simple method. I can say that x1 is equal to the determinant of matrix, a certain matrix that I will tell you what is this matrix, over the determinant of matrix A. He said that I just have to get x1, I just have to get the determinant of matrix that I get by replacing the coefficients that multiply x1, which are a11, a21. I can replace them by the column result. Okay, b1, b2. So if I put instead of these coefficients b1, b2, I will obtain a new matrix, and I keep the second column as it is. If I get the determinant of this matrix, and I divide it by the determinant of matrix A, which is this one, I can get x1. Similarly, to get x2, I can say that I can get x2 by just dividing the determinant of matrix 2 obtained by replacing the coefficients that multiply x2 by the result column, which is b1, b2. So I will get here a11, a21, I will keep them as they are, and I will replace the coefficients of x2 by b1, b2. I get the determinant of this matrix, and I divide it by the determinant of matrix A of coefficients. I get x2. Okay? And you can mathematically prove this rule. It's very simple. You can solve your system as, because you know substitution techniques, you know a lot of methods from school how to solve this system. You can verify that by putting this form, you'll get exactly the same result. Okay? Now, this method will become more complex if we get a higher number of equations. Because, for example, if you have a 3 by 3 system, already the computation of the determinant will become more complex. Because here, let's say, if you want first to transform from linear system to the form A times X plus B, what do you have? First, we said the coefficient of x1 will constitute the first column. The coefficients of x2 will constitute the second column. And the coefficients of x3 will constitute the third column. And the, of course, equal to times the variable column, x1, x2, x3, equals to the results column, b1, b2, b3. Now, if I want to compute the determinant of matrix A, the technique is I put plus, minus, plus. So I alternate sign, and I start with the first element will be plus A11 times. I drop the column of A11, I drop the row of A11, the matrix remaining will be the following one, A22, A32, A23, A33. Then I will multiply A11 by the determinant of this matrix, which is very simple to find. It's A22 times A33 minus A33 times A23. Now I move to the next element. So minus A12 So now minus A12. Now I drop the column of A12, the row of A12. I will have the remaining terms will be A21, A31, A23, A33. So I determine the determinant of this matrix. And the final term will be plus A13. Now I drop the row of A13, I drop the column of A13. The remaining terms, I will get these four. So I get now the determinant of this matrix, which is A21 times A32 minus A31 times A21. So as you can see here, the determinant expression now is much more complex. And if I move to a larger system, well, it will be very, I will take a lot of time to compute it. Because imagine you have 4x4 system. I will follow exactly same procedure. The procedure is not hard. It's a simple procedure, but it will be very long. And here, plus, minus, plus, minus. I start by plus A11. I drop the row. I drop the column of A11. This will be my matrix that will remain. I put it here. I should determine its determinant. The next element will be minus A12. So now I drop the column of A12. I drop the row of A12. What are the remaining elements? These ones, they will constitute a matrix of 3 by 3. I put it here. I move now to the third element, plus A13. I drop the row. I drop the column. The remaining elements will be these. They form a matrix of 3 by 3. I put it here. And then finally, I have here plus, minus. So the last term will be minus A14. I drop the row, I drop the column. I have times the determinant of this matrix. But now already, to find the determinant of a 3 by 3 matrix, also it needs time. So now here you can see for each one, we did it in different colors in order to see that each term will expand into a high number of terms. So here, to get the determinant of this matrix, I will do the conventional way for 3 by 3, plus, minus, plus. So the first term will be A22, I drop row column, these four terms will remain, etc. So you see that it will take a very large time to compute the determinant of a 4 by 4 matrix. Imagine now it's 5 by 5, it's never ending. And you will need a lot of, the exam will finish and we will not finish to get the determinant. This is why we say that the Cramer rules will only be used in case you have 2 or 3 equations. For more equations, it will be, no, of course, I will not give it an exam. Don't worry about it. Okay, because it will need a lot of time. Yes, exactly. So we will just work with Cramer rules for 2 equations or 3 equations, not more. Okay. And then, in case I have 2 or 3 equations, the Cramer rules is as we said. I just replace. So here, the technique is illustrated here. So you just need to find x1. It's determinant d1 over d, as I told you before. You replace the column of coefficients multiplying x1 here. You get and you divide by the determinant of the coefficients, the matrix of coefficient A. And to get x2, you do d2 over d, which is a11, a21, b1, b2. So you replace now the column of multiplying x2, and then you divide by determinant of A. This is Cramer's rule. You can apply it for any number of equations, but it will not be efficient if you have more than 3 equations. Okay, so here you have the example. We will do it next time. We will see how we can use the Cramer's rule to find the solution of a system of 2 equations. Okay, any question on this?
No, doctor, thank you.
Okay.
Doctor, the first 10 slides you were talking, how do we put the system? Are we responsible or no?
No, you will not. I'm just linking this course to other courses. I want you to see the benefit of these numerical techniques. In this course, I don't predict that you know all fields. Maybe you don't have a knowledge in electrical field, or you don't have a knowledge in thermal field. I don't know. So this is why here, whatever your discipline, you will benefit from this course, because I'm just telling you that you will face these systems in any field you are in. Okay.
Thank you, doctor.
Okay. Any other question? Okay, so we continue next time. Bye.
Thank you, doctor.
Welcome.
Bye.
دكتور
Yes?
Thank you, doctor.
بس بقدر أسألك سؤال بخصوص chapter 5.
Yes, sure, بس بعد في less than 1 minute. If you want, you can ask me by
يا دكتور
WhatsApp.
هو اوكي مش مشكلة دكتور. ثانك يو.
هلا if you want إذا سؤال صغير تراي يعني إذا كان
هو
قطع
كان بدي
شيء.
أسألك بس بالجراف لما تقولي لنا إنه which method is the best مثلا بس
Yes.
بنقول لك إنه مثلا الفولس method because the graph is linear بس هيك ولا لازم نحكي أكثر؟
Because the behavior of the function is close to the linear profile. Yes, you can just say that.
بس هيك يعني.
Yes, yes. It's one
بس
sentence
قولي
of
لنا
justification.
compare the two methods